Thanks a lot, guys, for coming to our talk today. Today, Phil and we're going to be presenting an overview of our Hippo project at Credit Suisse, and particularly how we've been using Cassandra to solve some of the challenges that we faced. So I want to give a bit of a history behind this. Around about 2009, 2010, within equity derivatives, we had a number of risk systems within that department. And functionally speaking, they all did a very similar job. And I think it's fair to say most of the industry was still feeling the effects of the financial crisis from 2008. So the decision was made to effectively consolidate all these risk systems into a single one. And this new risk system required a service where it could store all of its data, like market data, trade data, and things like that. So that's what Hippo is, basically. So it's a web service. It exposes its API using JSON over HTTP, and it has a number of clients. So obviously the main client being the risk system itself. It saves market data, trade data into Hippo. We also have the trading UI as well. This is the main interface that our users see to the risk system. And we also have the results store as well. The results store is used to feed risk and valuations to other parts of the business. So can I just get a quick show of hands to see who comes from a risk management sort of valuation background from an IT perspective? Okay, a few of you. For those who aren't aware of what a risk system does, generally speaking, they do a similar thing. In our case, a risk system is used to risk manage a portfolio of trades. So a given sort of valuation within the risk system, the first thing that happens is the trader will go out and refresh all of the data. So market data, trade data, they'll go out to live sources like Reuters, Bloomberg, grab all that data, and that data then gets persisted into Hippo. The next thing that happens is the trader makes some decisions about that data. They might decide to bring some of it in, all of it in. They might decide to override some of that data. And once they've made that decision, that data is then tagged. And I'll go into a bit more detail about what a tag means in terms of Hippo. And a tag basically represents the entire universe of data that's required to value that portfolio. It's quite an important concept within Hippo. So once the data's been tagged and the calculations have been run, you can then view the results. And this happens a number of times, hundreds of times during the day for a given portfolio, and we have thousands of portfolios. So I guess the point I'm trying to get across is, while the name might not suggest it, but Hippo is a very important component within this risk system. And it's involved in the main sort of aspects of risk managing a portfolio. The only one that isn't involved in is obviously the human interaction when it comes to making decisions about the data. So obviously, developing this new system, we came across a number of challenges. We're going to cover a couple of them in this talk. The two main ones are high availability and scale. Keep in mind, we were going from a number of risk systems to the one risk system. And in the past, if any of those risk systems went down, then it would really only impact the users of that particular risk system. In the new world, where there is only one risk system, if that one risk system goes down, it's going to impact all of our users. And the other thing is scale as well. We need to make sure that as we migrate more and more portfolios onto this risk system, it's not going to impact performance, and also from a cost perspective as well. So now, I'm going to hand it over to Phil. He's going to go into a bit more detail about how we solve some of these challenges.
So, as Jay was mentioning, it's obviously very important for the traders to see their risk, because if they can't see that, they can't hedge positions, and they'll lose potentially a lot of money. So, for us, the availability is a very important thing, and we want to use Cassandra to solve this problem. So, we've got two types of downtime, as most of you will have, I suppose. That of unplanned, so things like losing a couple of boxes in a cluster, or like network outages, that sort of thing, and planned downtime. Now for us, there's sort of regulatory commitments where you have to do things like DR tests to show that you're a sort of stable application and that kind of sort of stress testing thing. So we approach this by having the following topology. So on the far left, you can see we've got a HA proxy software load balancer, and we have 2 data centers in a region. And we've got 3 regions, so we've got 3 setups like this. So the Hippo is a Java app, as Joe was saying, and then that talks directly to the Cassandra clusters. As you can see here, we run an active-passive approach. Now, the main reason for this is because, I'll talk a bit later about active-active, but we found initially that there was a bit of latency and we weren't always getting back responses that we needed from the other DC. And then in the Cassandra itself, we have a local quorum consistency and a replication factor of 3. So with this kind of approach, this works pretty well for getting that kind of uptime, because then if the trader notices there's some kind of problem, they can sort of mention to support, and then we can come and manually intervene or flip the DCs. And that's fine, but that can take quite a long time. So we thought, well, we want to make this better, because if it takes like half an hour for them to notice a problem, that could be really damaging to our positions. And so for us, the obvious way to make things better is to automate everything. So the way we do that is, at the minute, we're using the Hector driver for Cassandra. So under normal operations, everything's fine. The Hippo is talking to the cluster. Then when we lose a node, the Hector driver informs the Hippos we've lost a node. And so they're aware of kind of how many they've gone down. But everything's still fine because we've got that replication factor of 3 and the consistency of local quorum. So we've got enough nodes to run along in that DC. If we lose another one, then we decide it's time to switch over to the other, make the other one active, and that automatically happens. All the Hippos decide to go to the other one to write and read to the other one. And then in the meanwhile, we can figure out what's wrong with the passive DC and fix that up. Now this has worked really well. We're a small team, there's 4 of us developing this app, and this is like a really important kind of application, and we've not really had to do much, any intervention in this kind of stuff. So when it comes to planned downtime, we could just rely on this, but we thought if you're going to have to take a DC down for whatever reason, you may as well have a way of doing that ahead of time. So on our little status page, we implement a little switch, so we can just switch between the 2 DCs, again using the Hippos. And then we're talking about this as like a big thing, so how often do we actually do this? Well, we looked at a 3-month range, and you can see where the colors varies when the switch happens. So you can see here, there's actually 6 times in 3 months, which is quite a lot when you think about it. I think that's like once every 2 weeks or something. But in terms of what we noticed, we sort of came in and go, look at this graph, it's changed, and there's no intervention required by us, because Cassandra really allows you to be up all the time with very little effort required. So, of course, it's really great having an app that's up all the time, but if you're scaling down all these different systems into one system, compacting them all into one system, you really need to handle all the load you're going to put on it. So probably a more complicated challenge is how do we handle all the scale from the other systems?
So we've sort of solved the high availability problem. Our next challenge was, keeping in mind we were migrating a number of portfolios onto this risk system, we wanted to make sure that we were going to be making the best use of our storage that we have. TCO was a total cost of ownership. It was a big sort of a driver in some of the design choices that we made. So one of the options that really wasn't available to us was to just continuously expand our Cassandra cluster at the same rate of new trades getting migrated. So we had to look at the data that we have in Hippo, and I'm just going to introduce two concepts that we have. The first one is called gallerification. So this is when we effectively store market data within Hippo. So here's an example of what that market data might look like. In this case, we're looking at an Apple stock price. The risk system would tell Hippo, here's some market data, please can you go and save it and give me back a reference to it. And behind the scenes, what Hippo does is it will take this and it will check to see if it already has an Apple stock price. If it does have an Apple stock price, then it will see if this new stock price is different to the one that it already has. If it is different, it will save this data and it will return back a reference to the client so they can pull it back out again. If the stock price hasn't changed, then we have a bit of an optimization and say, well, since it hasn't changed, we're not going to save this bit of data. We're just going to give you a reference back to what we already have. So that's how we store market data, trades, anything. I mean, and I guess the Hippo doesn't really model any of this. It just takes the JSON data and stores it within Cassandra. And Cassandra's sort of a flexible sort of schema design allows this to happen quite efficiently. And the next concept is tagging. I sort of referred to it briefly before. A tag is effectively everything that's required to value a portfolio. So in this case, we're looking at two things in the tag. It's a map. You can think of it as a map. We're looking at the Apple stock price and the GBP USD FX spot rate. And every time a valuation is done, a tag is created, and that tag is then effectively valued. You know, in this case, we're looking at just two elements in the tag. Realistically speaking, there's hundreds of thousands of elements in a tag that make up all the tiny bits of market data that is required by the analytics to build the market data and then value that portfolio. And this data that we have sort of falls into two categories. The first category is short-term data. It's quite transient. And if you in a real-world example, during intraday usage of the risk system, a trader will value the portfolio hundreds of times. So he'll value his portfolio the first time, he will look at the data, and once he's finished looking at that data, he'll value it again. So the data that was associated to the first valuation is now effectively stale and is no longer, won't be referred to again. The other type of data is long-term data. So long-term data is quite special because it's data that is then used to feed down to other risk systems, so product control, risk management, these types of business areas. So long-term data we need to keep for a longer period of time in Hippo. It can be anywhere between 30 days to 7 years. The interesting thing about long-term data is Hippo doesn't know it's important at the time of inserting it. So that was one of the issues that we had to work around. So, you know, we have short-term data that we don't want to keep around for a long time, and we have long-term data that we want to keep around for much longer. So we thought, how do we handle this problem? So one option could be Hippo could go ahead and delete the data, right? I mean, you can schedule something within Hippo, and it would try and figure out all the runs that were done, you know, in the last couple of days or whatever, and then it would go ahead and just delete that data out of Cassandra. However, there's, you know, this type of model has a number of complexities around it. You know, how do you handle failure scenarios? How do you handle some of the edge cases in the sense that if one data is referred to by multiple tags, how do you deal with orphan data? It's quite complex. It's not such a straightforward problem to solve if we were to go down this approach. Thankfully, Cassandra TTL came to the rescue. So what we do is any data that gets inserted into Cassandra has a default TTL of 6 days. So after 6 days, if nothing is done to that data, it will appear to be deleted to the users. And then behind the scenes, Cassandra will mark it as tombstone data, and then it will eventually get compacted away. And this has been a great savior for us in terms of managing the amount of data that we have. You know, as it turns out, when you have a very fast, efficient data store that can save data very, very quickly, you end up having a lot of data very, very quickly. And TTL is a great solution for us. Now, there's also this problem of long-term data. I did mention that long-term data isn't this sort of special data we don't know at the time of inserting it. So we introduced this concept of immortalization. So when a user has done a valuation and they decide that that data is important, they immortalize all the data that's associated to that valuation. And what Hippo does behind the scenes is it effectively rewrites that same data back into Cassandra with an extended TTL. This works great for us because a very small proportion of our data falls into this special category.
So, as Jay was mentioning there, having a minimal set of data can really help keep your costs down, but also help improve your performance. Now, I don't know, I think I recognize some of you from the course of performance tuning yesterday, but one thing they kept mentioning was the data model. If your data model isn't very good, then your performance won't be very good. So how do we improve performance? We have to make sure our data model is sound. So when you're valuing a portfolio, there's a couple of steps that we go through. So firstly, the gallerification, which is when, as Jay showed you, those resources get written to like a gallery table. And that takes, on average, about 50 seconds for all of the different pieces of data. And the Hippo is quite chatty, so for every resource you have a single HTTP call. And in that way, if it fails, you get a quicker replay for the failed element. Then, after that's happened, you create a tag, so when the trader wants to value something, he makes that tag, that universal snapshot of all the data that he wants to use. Now this takes 150 seconds on average, and then finally, that gets fed in to the calculations, which is like a library another team provides us that takes all the data and figures out what their actual risk is. So in total, that's 500 seconds, which is quite a long time. So if you've got, you think of your trader, that's almost like 10 minutes of him just sitting around doing whatever else he does. And 30% of that time was spent on creating the tag. So we were thinking, well, why is that so slow? So we started looking around at what was happening on the disks, and we also noticed that even though we'd done that long-term, short-term sort of TTL fix, the tags were all occupying a lot of space. So we wondered, why is that as well? So when we looked, there wasn't really any overlap between them in the sort of tag table that we had. But on the gallery table, there was lots of overlap, because as Jay mentioned earlier, when you gallerify something, if it's already there, we don't rewrite it. And so lots of different tags could use that bit of information. So we thought, wouldn't it be nice if we could have a tag that's if it's a bit like the old one, then it reuses a lot of the stuff from the old one and just updates, just updates what it needs to. So initially, our data model was a bit like this, where you had a wide row, and you wrote every single reference to the gallery table. And if you had another one, you'd write all the references again. But you can see in this example that really only one thing has changed there, which is that FX rate. So we thought, if we normalized, well, the problem with this as well, we found there was a lot of hotspots trying to read it out and things like that. So we introduced another table, and we sort of normalized it a little bit. So the next column family or table, we grouped a lot of those resources, so then a tag's able to reuse all of that data efficiently. And so you can see there the FX rates now are both part of one row, and again these will be wide rows with all your different resources, so you can have as many as you like. And you can see now the top level tag links to those resources, which in turn would link to the gallery and give you the actual JSON blobs, because those JSON blobs are like many megabytes big. So it's not a trivial thing to just slam them all into one massive wide row, for example. So we call this delta tagging, which is when the user says to us, I want a new thing. It looks a lot like this old thing, but there's only these little bits are different. So then the new way of doing that, using our data structure, is now it's got the keys there. And we want to so we reuse the keys. And then we add an additional row to the taglet group, which you can see has got the grouping of the resources. And then you pop that in to the top level tag. So then we did a little bit of performance analysis, and we actually came down to 5 seconds from that 50 seconds just by changing the data model to do this, which, it's like 145 or something second saving. And in terms of the tagging, that's a 97% increase in speed just from getting that data model a bit better. Now, when we look at the overlap in terms of disk usage now, instead of being very separate, the tags actually, there's a huge amount of overlap. Now, this is particularly relevant for, we've got a different use case from the traders, where overnight, people will run like an automated batch of runs where they alter one bit of data every run. So they might run 1,000 of those overnight for one profile. As Jay said, we've got hundreds of profiles, so there's hundreds of thousands of runs happening, where actually only one bit of data is changing each time. So this allows us to be very efficient in terms of what we're storing and what we want to value. So pass over to Jay to talk a bit about the ops challenges we were facing as well.
Yeah, so from the ops side of things, one of the main benefits that we've really had with Cassandra is the fact that sharding data is effectively within the DNA of Cassandra. So that's allowed us to do basically just-in-time cluster expansions. And this is really like the secret sauce behind Hippo in allowing it to scale and meet demand of all these migrations that we were doing exactly when we needed it to. And like if you were to compare it to traditional, I guess, relational technologies, if you knew you were going to sort of start this big project where you knew you were going to migrate all these RIS systems into one RIS system, you would generally try and get your hands on the biggest bit of hardware that you can to run your relational database. But the advantage of Cassandra is we didn't need to do that. This line is kind of like a trend line of the number of trades that sort of increased on our RIS system as time went along. And this example basically shows that initially we started off with a cluster size of 3. Within a specific data center, and then as soon as we knew that we were getting quite close to sort of the limit of how much data and performance we can handle, we increased that cluster size exactly when it was required to be increased. So then we went from 3 to 6 to 12, and that's been great for us because this is also running on very normal sort of VMs, nothing special, and from a cost perspective, it's been great. The other issue is consistent performance. We have a number of clients. I mentioned before the RIS system, the trading UI, the results store. They all depend on A, Hippo being there, and B, it being and returning data very, very fast and at a consistent sort of rate. So just some tools that we use to help us track our performance metrics. So we use a combination of Logstash and Kibana just to allow us to do log aggregation across multiple computers, Cassandra's, all the Cassandra nodes, and all the Hippo nodes as well. And we're very big users of Graphite as well. I've just got an example graph here that I can show you of how we're using this. In this case, we're using Graphite to monitor our performance. So the top graph is basically showing response times from the Hippo sort of endpoint perspective, not the Cassandra, but obviously it does also include the Cassandra performance as well. So there are 3 lines there. So the green line is measuring today's performance, the purple line is measuring yesterday's performance, and the sort of light blue line is measuring the performance 7 days ago. So as you can see, it's all tracking relatively well. So today it's 9 milliseconds, yesterday it was 11, and 7 days ago it was 11 as well. And the below graph is showing you the throughput as well. So the throughput is roughly similar as well. So this is when things are going good. When things are going bad, it begins to look a bit like this. So you can see here around about Tuesday at 4 a.m., the green line started to trend a lot more higher from the other 2 lines. And then ultimately around about Wednesday at 12 p.m., things started to settle down a little bit back to normal. And we use the throughput as well, just as another measure to make sure that, that isn't a result of the throughput having doubled or trebled or whatever. Incidentally, this particular issue was down to an issue we had with our storage layer. We are using SAN storage. I know that's a big anti-pattern, and we are actually moving off of that onto physical local storage. So if you want to know how SAN can impact your app's performance if you use a Cassandra, that's a good picture of what that looks like. From a maintenance perspective, I guess there really isn't much to say on this topic, and I think that's a good thing. Cassandra generally just handles itself, right? I mean, we don't do a lot of maintenance, and Phil said we're a small team. There's only 4 of us who who develop and sort of support Hippo, and we have a number of other very important applications as well that the team looks after. There's 2 main things that we do. We run regular repairs once a week, less than the GC grace period, and we also we carry a 2-day window of snapshots as well, just because A, it's very cheap to create a snapshot within Cassandra to back up that data, and B, if the worst does happen, at least we have a starting point to restore that node from.
So finally, just want to quickly go through some lessons we've learned. We've had this system in production for about, I think, 4 years now. And One of the main things is that Cassandra is changing very quickly, and you saw some great improvements coming out from Jonathan Ellis this morning. So one thing is to constantly kind of reevaluate what you're doing and how you're doing it, because just because it worked a couple of versions ago might not be the best way of doing it in the new way. So for example, I told you that we were running that passive-active kind of DC approach, but we're again going to reconsider the active-active approach, particularly because now the data stacks driver allows you to do things like customizable consistency policies, letting us do things like having a local quorum and then falling back to quorum if you need to. So we are thinking of going to something like this, because as we migrate more and more of those systems, we're noticing we're getting a lot of read pressure. And hopefully by using the second DC as an active DC, we can alleviate some of that. So really I think you really need to look into Cassandra if you're using it in your production system and try and really understand how it's working. But in terms of the solution for our problem, it's definitely been stable and reliable. And I think with using Cassandra, you could definitely make an application that will last 4 years, 5 years, or maybe as Zohar said, for the next 20 years even. And with that, I want to thank you for listening to our talk and take any questions you might have. Yes. One at the front.
Do you have any real-time use cases, or is this mostly batch processing and portfolio analysis?
This is, so our intraday use case is, it's an equity derivatives risk system. So the model is more complex trades that are getting valued rather than a high frequency of that trade valuation.
You mentioned 5 seconds, 50 seconds. What's the data set? Like how many terabytes of data without that?
So if you were to look at a tag, if you were to sort of download a tag from Hippo, the on-disk size of that tag can be anywhere between 30 to 70 megabytes. That's one tag, that's one valuation.
What is the total data? This is a petabyte of data?
Oh, you mean our node size?
No. Well, the total cluster itself, we've worked out, is about 7 terabytes for that one, and it replicates across. They both obviously have that.
How many nodes you are using in the cluster?
So it's a 12-node cluster, yeah. And like I say, we've got 3 of those clusters across.
Yeah, we run this globally
so
across all.
they're all roughly a similar amount of data.
Question there?
What kind of consistency levels do you use for use cases?
So consistency is a big deal for us. So we always write and read at local quorum.
You mentioned that decision making, that analytics point of view. Are you doing in database, visual analytics, or in memory analytics?
So that, I think, do you mean the slide at the beginning? The decision making is done by the trader mostly.
Yeah.
So the trader will decide if they want to hold data or not, and they just feed it into the Hippo. So a lot of they kind of look at what they think is going to happen to hedge their positions. They will do a lot of the decision making. So it's not really, Hippo doesn't really make the decisions for the traders.
And often the general use case is when they refresh their market data, they don't want to revalue that portfolio with brand new data all the time. They might be only interested in vols at this particular point in time and then move on to spot prices and things like that. And it's down to them how they want to manage that.
Yeah.
Yeah, so you mentioned you have some kind of automatic failover mechanism and you're using local quorum for access. So how do you make sure that clients are kind of agree on what data center they're actually connected to? How do you synchronize that among clients?
Join it.
Well, I don't mind. The Hippo, they all write to the Hippo. So the Hippo, the app is like the only client for the Cassandra rings. So all of our clients talk to the Hippo first, and then the Hippos itself will, I guess they propagate through to each other through the Hector driver talking back to the Hippo. So it tells them the node is down and they switch. They know they've got they know kind of their DC aware of where the nodes are. So then they'll switch to the other DC. Also,
on the Hector side of things, we've implemented our own load balancing policy to detect nodes going down. So and that load balancing policy is aware of our Cassandra topology, and it will, if it detects that there isn't enough nodes to maintain a quorum, then it will, all those nodes will eventually, in a matter of seconds, then flip over to the other DC as well.
Okay, so can I guarantee that you don't get kind of split brain scenario where client?
We haven't seen it. I mean, there will obviously be a blip. There's a chance of there being a noticeable blip, but we've noticed that to be in the seconds rather than if it was a manual thing, it would be in the minutes or tens of minutes.
It sounds like your application is kind of single tenant in terms of the business. Have you explored having, I suppose, multi-tenancy, multi-use
No, I mean the use case is getting spread out to the general equities group, but the tenant will only be our risk system.
But have you tried to, when that happens, you thought through in terms of how you prioritize or ensure you don't get noisy neighbours even within the same business?
No, I mean, no, we haven't really looked into that. I mean, within our UAT setups, we have a number of key spaces for different use cases. So that's the closest that we have to multi-tenancy.
You touch on sandbox and proprietary system. What is the
Sorry?
Sandbox and the proprietary system? You were saying that you want to move to...
Oh, the SAN storage? Yes. Yeah.
Why is that?
I think just much more consistent I/O throughput. Because SAN is obviously shared amongst other people as well, which we don't have any control over. So having local disks is just much better for us.
Yep, go there.
So in an environment with tunable consistency, can you guarantee the same query always generates the same results?
Well, we're writing at local quorum and we're reading at local quorum. So, yes. We're not really leaning on the eventual consistency element from, like, you know, if we only write at quorum and read at 1 or anything like that. We only ever write and read at local quorum.
But you only ever use one data set for that?
Currently, yes, yeah.
So do you anticipate that will be a problem with...
When we use active-active?
Yeah.
Well, I think in our case, a lot of the data doesn't change all of the time. So if you imagine like a stock price or maybe a vol surface, for example, that's not going to change all of the time. They might change 100 times a day, but that sort of the delay in between that data changing is enough for that replication to happen across the other data centers. So we're not too concerned about that. And if we don't find it in that data center, we're going to then obviously fall back to the other one, which should have the data set.
We could take one more question.
I think.
I think that's what the lights are about. Yeah, chap there.
How do you handle the cross-regional consistency? You mentioned you had 3 different regions.
Yeah, so...
Yeah, so at the minute then, so they are separate clusters, so we don't have one massive kind of global cluster. So in terms of what they store, they are distinct, so there isn't really a consistency problem between like US and APAC, for example. So it's a similar, so that setup just is, we've got 3 instances of that setup and they are independent, so.
So when you're doing a global close thing, they run with local portfolios.
Sorry, when you were on global.
When you say a global close, when you're doing the reg reporting and stuff, are you running a portfolio in the region its own?
Yes.
Yes.
Yeah.
Okay. Yes.
And you don't guarantee consistency in market data between regions?
No, they don't even talk. The
they're
clients
separate.
from one region don't talk to clients in the other region. Yeah.
All right, well, thanks for listening, guys.